All right, welcome to another great episode of SchmidtChem. We're looking at AP topic 5.9 or unit 5.9, pre-equilibrium approximation. And in our last video, in our last series, we went over 5.4, 5.7, and 5.8, learning how to write rate law expressions from the elementary reactions in our reaction mechanisms. Today, we're going to go ahead and extend on that with pre-equilibrium approximation. And what that looks like, if we look at our learning objective, is that we just have to identify the rate law from a reaction mechanism in which the first step is not rate limiting. And so we've talked about the rate limiting step last time being the slow step. And so we can determine that very easily. And then in our last assignment, what we saw was when we wrote our rate laws that all of the reaction mechanisms that we used, the first step was the rate limiting step. But today, that's not going to be the case. The first step is not going to be rate limiting. And so we have to see how to handle those type of situations. All right, with that, let's go ahead and get started. And so as we look through this, we see that rate laws and non-rate determining rate laws and non-rate determining first step. So when determining the rate law from a reaction mechanism, the following principles apply if the first step is not the rate determining step. So when the first step is not the rate determining step, and we know the rate determining step is the slow step. So what we have is a pre-equilibrium assumption. Since the first step is fast and not rate determining, it is assumed to be fast. It is assumed to be a fast reversible reaction that quickly reaches a state of dynamic equilibrium. Now we have 2 units in AP chemistry where we talk about equilibrium. Here we just need to look at it on its most basic definition. And when we look at equilibrium, its most basic definition is that the rate of the forward reaction is equal to the rate of the reverse reaction. And what this is going to do, this entire expression right here is going to help us write our rate law for when the first step is not the rate determining step. Now here, this equality allows for the relationship between the reactants and the reaction intermediates to be defined by the equilibrium constant expression for that first step. This is something that we may talk about when we get into unit 7 and 8, but right now we don't need to necessarily speak on it. But notice the equilibrium constant as a capital K. Do you notice that? That is not talking about our rate proportionality constant. So that's why that is a capital K. That is not looking at the rate constant. As a rate constant, or the rate proportionality constant, is a lowercase k. All right, so elimination of the reaction intermediate. This is the most important part of today. And so I'm going to just go ahead and front load this before we even talk about it, is that when we write a rate law, the rate law cannot include a reaction intermediate. Last class, we were able to identify reaction intermediates and catalysts, but this time we have to identify those reaction intermediates because we have to be able to identify that they're in our rate law and that we have to remove them. All right, or we're going to have to find a process so that they do not appear in a rate law, because your rate law cannot include a reaction intermediate. All right, so the intermediate in the rate law must be based on the slow rate determining step. If we see the rate law will invariably contain the concentration of a reaction intermediate, a species produced in one step and consumed in a subsequent step. So what we see is when we have a reaction in which this rate determining step is not the first step, then we will end up having a reaction intermediate in our rate law. And we have to do something about it. Number 2, it says that a valid overall rate law cannot contain reaction intermediates. I've already said that. A rate law cannot contain reaction intermediates. So how do we deal with that? We use a process called substitution. And because the rate of the forward reaction equals the rate of the reverse reaction, we can go ahead and replace our reaction intermediate by algebraically isolating and express a value expressed in the terms of the initial reactants. And that will help us get our final rate law. Okay, so let's look at and see what this looks like. So before we get into what that looks like, we're going to go ahead and just go through our whole scenario, kind of go back just a little bit, and then we'll touch on what that looks like. I would probably should go over the concept immediately, but we're going to just work this as one big problem, and then we'll get to that main point, and we'll make sure we're there. Unbelievable. All right, so all right. Oh no, it changed. Good goodness. Unbelievable. All right, so here we are. We're looking at first some data to determine this is our overall reaction. We want to look and see what the experimentally determined rate law is. Do you know how we define the experimentally determined rate law? We look at experimental data. And we looked at this before, and this looks a lot like the method of initial rates, as we see initial rates there. And so before we go looking at our proposed mechanism, we're going to determine what the experimentally determined rate law is. And so things that we need to pay attention to. All right, one of those things. There you go. Welcome to live TV, my friends. All right, there we go. All right, so one thing we're going to have to do is we're going to have to determine the rate law with respect to NO. So what experiments are we going to use to determine the rate law with respect to NO? Anyone know? Surely we know. Yeah, we're going to use 1 and 2. We're going to use 1 and 2. Why is that? Because the initial concentration of O2 stays exactly the same. So this change right here is causing this change right here. And if we know what how the rate is affected by the change in the concentration, then we can determine the rate law. All right, so this is what we're going to look at is the concentration of NO. And we know that it went from 0.2 or 0.1 to 0.2. It changed by a factor of 2. And then when we look at the rate, we see that the rate, notice these are both times 10 to the negative 4. So I can just say 4 over 1. So it changed by a factor of 4. So what rate law is that? We have the concentration changed by a factor of 2, but then the rate changes by a factor of 4. That is going to be second order. All right. And so we can go ahead and write our rate law as being rate or not. Okay. Rate is equal to K NO squared. Now, maybe we should put that as rate. Now we're going to look at this in terms of O2. When we look at this in terms of O2, what experiments can we use? We need NO to stay the same while O2 changes. It's going to be 1 and 3. So we're going to look at 1 and 3. And so we're looking at these. And we see, again, the concentration change is going to be 0.2 over 0.1. That changes by a factor of 2. And the rate, notice they're both times 10 to the negative 4. So I'm just going to use the coefficients. And so we see 2 over 1, which is 2 times. So, so the concentration changes by a factor of 2, and so does the rate. What order is that? What order is that? It is first order. And on that last quiz I just gave, that was missed highly. People told me that was 0 order when they saw that situation. And so notice that the rate change is directly proportional to the change in concentration. That is first order. That is first order. So we would then write our rate law as O2 to the 1. All right. And so that is our experimentally determined rate law. All right. Now we're going to get to our reaction mechanism and get to the main part of today. Another thing that we want to look at is, before we even start doing the other part, is do these elementary steps add up to the overall reaction? All right, do the elementary steps add up to the overall reaction? So let's look and see if we can do that. What are we eliminating before we add? So just tell me what it is. N2O2. And what is N2O2 considered? A reaction intermediate, because it's produced and then it's consumed. Do we see that? We don't have a catalyst in this one, but we have a reaction intermediate. N2O2 is consumed. Is anything else going to be eliminated? No. All right. So what we see then is on the reactant side, NO plus NO, which gives us what? 2NO plus, it should be a capitalized O. It was, but I don't know why I'm having issues with this, but there we go. And then plus O2, and it yields what? 2NO2. Now, if we look at our overall reaction, my computer does not pause. Evidently, it just wants to pause. So we look at our overall reaction, and there it is. It's the same thing. All right. So does that mechanism, is it valid in that it adds up to be the overall reaction? Yes. Now what we need to do is we need to write a rate law. And we need to see if the rate law that we write from our mechanism is consistent with our experimentally observed. We already found our experimentally observed rate law from using experimental data. Do you see that? The method of initial rates. So where do we write our rate law from? The slow step. So we're going to look at the slow step. Now, what do we notice about the slow step? It is not the first step. The last class, it was the first step. Now, what we just read in our notes is that when we have a slow step that is not the first step, what's going to happen is the first step is going to be in equilibrium. Do we see these double arrows here? So what this means is this reaction is going to meet or going to go into dynamic equilibrium and fairly quickly. And what that means is the rate of the reaction going in the forward direction, where reactants produce products, is going to be equal to the rate of the reverse reaction, where products produce reactants. Do you see that? And so the rate going this way is equal to the rate going that way. All right. And that is a major principle for why we can use substitution, because the rate of this going that direction is the rate of this going that direction. All right. So we're going to write our rate law from the slow step. What is our rate law from the slow step? Just write it out. Rate is equal to what? K into O2. What order is it? How do we know what order it is? The coefficient. What coefficient is in front of N2O2? 1, so this is first order. What if there were a 2 there? Then it would be second order. Then we see O2, and what order is that? First, because it has a coefficient of 1. Now our problem is that we just identified N2O2 as what? Reaction intermediates. What did our notes tell us cannot be in our rate law? Reaction intermediate. So we have a problem. Now, I will tell you this. Every time you write these rate laws and you see the slow step is not the first step, your rate law that you write is going to be incorrect, but you should write it. Your rate law is going to be incorrect because it's going to contain a reaction intermediate, but you should write it anyway. And the reason why you're going to write it anyway, because if you don't, you're probably going to leave something out. And you're going to feel so good that you got it right. And in fact, you're going to be very wrong. And I'm not just speaking because I've watched students do this. I do this. Okay? So I don't make those mistakes when I write this out. All right. And so I'm just telling you, this is a great method for making sure you do not make mistakes. So what we're going to do, we can't have a reaction intermediate. So what we know is this is our reaction intermediate, but we also know the rate here, or the rate in producing this reaction intermediate, is the same or equal to the rate going this way. So what we can say is N2O2 is equal to NO plus NO. And so what we're going to substitute into O2 with NO plus NO. What's another way of simplifying NO plus NO? 2NO. That's very easy, right? 2NO. So now we're gonna go back and we're going to rewrite our rate law, and we're going to just simply substitute into O2 with this. So how can we express that? NO, and then that has a coefficient of 2, or there's 2 of them. So what are we going to say? It's second order. And the reason why you are writing this with the reaction intermediate, because let me tell you what happens. I'll tell you the story. You're gonna look at this. It's going to be a multiple choice question. And you're going to go over here and you're going to be like, I substitute into O2. Oh, great. That's going to be rate equals KNO squared. And you're going to feel so good and you're going to feel like a genius. And you kind of are. But the problem is you're going to see a choice that says rate equals KNO squared. And you're going to feel good about being wrong, because we substituted into O2 perfectly, but what else belongs in that rate law? O2. We can't leave it out. You see that? We do need to substitute the reaction intermediate, but that's not at the expense of leaving O2 out. You see that? So if we write it wrong and then we show the substitution, then we'll remember not to leave O2 out. Does that make sense? And I promise you, you will leave it out if you don't follow my logic here. It's real easy to do, because we get carried away with doing the substitution. You see a choice that's there, you're kind of in a hurry, and then all of a sudden you chose the wrong thing. And so if you just are systematic, you're going to get that correct every time. Let's look at another one real quick. And I'm going to skip over this one. I'm not going to put that one in the video, but let's look at this one here. Let's look at this one here. The reason I'm not putting that one in the video, I showed other classes, but I'm not going to put it in the video because it has orders that are not 0, first, or second, and that's not necessary to share with anybody else. All right, they don't deserve it. All right, so unless you like and subscribe. All right, so if you like and subscribe, you send me a request, which I don't take. I would definitely go ahead and show you that problem. All right, so let's take a look at this next one. And the first thing we're going to do before we write our rate law, let's determine our experimentally determined. Oh, by the way, I need to go back just real quick. Did this rate law match our experimentally determined? Okay, NO2, O2 to the 1. Yeah, it does. All right, so that's a valid mechanism. All right, so it added up to the sum of the elementary steps added up to the overall reaction, and then the rate law from the mechanism was matched the experimentally determined. So I will tell you that normally you won't see a lot of people put the initial rate with this concept, but I'm not normal. All right, so we're gonna do it this way, because this is actually how you determine your experimental rate law, is using an experiment, and this is using experimental data. All right, so let's take a look at this. We're not going to be able to validate this mechanism because I didn't give you the full equation and all that, but we can definitely determine what the experimental rate law is. So what are we going to do to determine the experimental rate law? What do we want to start with here? 1 and 2. We're going to start with experiment 1 and 2, and what are we going to find the rate law for? That's right, A. Okay, because B is going to stay the same, and so we see a change in A, and then we see a change in the concentration, of the rate of A. That change right here, this change that occurs right here, is only because of the change in concentration between A. Now, I will tell you this. As I looked over quizzes, what I saw was people were telling me concentration. They were putting in concentration, and they would do something like this: 0.1 over 0.1, and they're like, the change in concentration is 1. If you're doing that, you're automatically wrong. And I'm going to tell you why. Because if you don't have a change in concentration, well, you shouldn't have a change in rate. All right? And then people would tell me, well, I did. It's 0 order. Well, what did you do? You didn't do anything. You have to have a change in the concentration. Do we see that there's a change in concentration here? Yeah. One other thing that I noticed is that some people were putting the smaller number in the numerator and the larger number in the denominator. You always want to have, if you want to get a whole number here. You want to get a whole number here. So if you're going to get a whole number, what you're going to need to do is put the larger value over the smaller value. So if we took 0.2 over 0.1, then we see it's easily 2 times. Do you see that? And it's just a little bit easier to figure out. And then we look at rate, and this is rate. And so notice these are both times 10 to the negative 4. So we can just say 2 over 1, and that's 2 times. So the rate, the concentration increased by a factor of 2, and the rate increased by a factor of 2. What does that tell us? What does that tell us? It's first order. So rate equals Ka to the 1. All right. Then we're going to go find B. We'll find B real quick. And we go to B. And which experiment should we use for B? Say again. 1 and 3. Why do we want to use 1 and 3? Because A stays the same in experiments 1 and 3. And B does what? It changes. So we have the change that we see between 1 and 3 is only going to be because of the change in concentration of B, not because of the change in A. A didn't change, right? And so that's the whole logic here. So again, we have 0.2 over 0.1. That's 2 times. Again, these are times 10 to the negative 4. So 4 over 1 is 4 times. So we see the concentration changed by a factor of 2, but the rate changed by a factor of 4. What does that tell us? It's second order, so this is rate equals KAB squared. Easy stuff, right? So that's our experimental rate law. That's our experimental rate law. And then I just want to be able to write the rate law from the mechanism. Can you write the rate law from this mechanism? Which step are we going to write our rate law from? 2. We're going to write it from step 2. Why step 2? Because it's a slow step, or the rate determining step. And so what we're going to do is we're going to write rate equals K. What are we going to put here? I to the what? 1. Why? As a coefficient of 1. A to the what? 1, because it has a coefficient of 1. Now, what's wrong with our rate law? I is a reaction intermediate. We see I is produced, and then it is consumed. Do you see that? So it is a reaction intermediate. And our rate law contains I, which is the reaction intermediate. Can our rate law contain a reaction intermediate? The answer is no. So how are we going to fix this? So good thing we wrote this down incorrectly, because now we're going to write it down correctly by substituting the value of I. It's no longer going to be I. I is now what? B. And what's the order on B? It is second order. Do we see that? Because it has a coefficient of 2. And then all we got to do is not forget our other guy, A, down here. You see that? We have to make sure we drop him. Otherwise, if we forget him, then we'll be in trouble. This is why we write the rate law incorrectly, so we don't forget those things that are not being substituted. Is that easy enough? All right. And so that is how we handle writing rate laws that have mechanisms in which the rate determining step is not the first step. It is the second step. I don't think we're going to see any that are the third step or the fourth step that become incredibly difficult at that point. But the first step, if the first step is fast and the second step is slow, all we have to do is substitute our intermediate for an expression that is equal to that. How do we know it's equal to that? Because this the first step reaches dynamic equilibrium, in which the rate of the forward reaction is equal to the rate of the reverse reaction. For now, thank you for watching. Let me hear those rings. Get those notifications, because these videos are fire. Please like and subscribe. Schmitty out. All right.